Right, so it'll take some time for people to start to filter in.
Sure.
So we'll just wait for a minute or two.
Yeah.
For those of you who are just joining, welcome. We'll start soon. Right. And as people start to filter in, welcome everyone to the fourth webinar in this lecture series. And we're very excited and very happy to have join us Dr. Elif Erdine from the Emergent Technologies and the MTech program at the AA. The Emergent Technologies program at the AA. She's the director of that program, and she's going to be talking to us about the applications of evolutionary computation in design. And this is something that MTech has been doing for quite a while, so we're super excited to have Elif join us. Welcome, Elif.
Hi there. Hi, welcome. Welcome everyone, and thank you, Mohammed, for having me join you guys. Nice to meet you all.
Thanks very much. I appreciate in London. It's, I think, 8 a.m. or something like that. So,
yeah,
and just
that's all right.
For those of, this is something that I struggled with when I moved to Australia. For those of you in Australia, the day in London never starts before 10 a.m. So 10 a.m. is their 8 a.m. So if you have anyone join anything before 10 a.m., that person really cares. So we're joining 2 hours before 10 a.m. So we're very grateful. So the Computation Architecture lecture series is curated by myself, David Pygram, and Tim Shork, who I'll ask to introduce themselves, and part of the Masters of Architecture program here at the University of Technology, Sydney. So Dave, over to you.
Hey, welcome everybody, and especially welcome and thanks to Elif. We're very excited to have you. My name is Dave Pygram. I teach in the School of Architecture. I do research with Tim and Mohammed in computation design and robotic fabrication.
Tim?
Yeah, welcome everybody, and welcome to campus. I'm for the first time actually on UTS campus since months, so it's quite a,
that's
amazing moment for me. It's very quiet here, but I'm excited to have you here, Elif, and thank you for doing that. And yeah, looking forward to this super exciting lecture. Obviously, there's lots of overlap conceptually from our ambitions. So over to you.
Thank you.
Right, I will stop sharing. And Elif, thanks again.
Thank you all for having me, for inviting me. And I hope you will enjoy this presentation. Maybe I can start to share my screen.
Yeah.
Kind of. Okay, 1 second.
Perfect. We see it in full screen.
You see it?
Yes. And just before you kick off, just if I can remind everyone, if anyone has any questions throughout the lecture, please feel free to post them in the chat or the Q&A, and we'll get to them after the lecture.
Okay, great. Right, so let's do this. I'm going to stop my video just to make sure, that there are no lags while I speak, if that's all right.
Yeah, sounds good.
And then I'll be back on again. So again, thank you so much for having me. It's really nice to be with you guys again. And it was also our first day back at the AA yesterday. So, I totally am with Tim on the excitement. It was really nice to see students back in the studio. It's been 16 months, so very excited to be back. So yeah, today, in today's talk, I will try to expand on multi-objective optimization as a generative design methodology across multiple scales of built urban and ecological forms. And as Mohammed has mentioned, in MTech, we have been using multi-objective optimization tools for many years now. MTech is one of the pioneers in the field. And Mohammed, obviously, he did his PhD at the AA, so he's, as you all know, one of the co-authors of WOLSI with a team of other MTech researchers. And what what the lecture will aim to demonstrate is the advantages of using such adaptable computational methodologies to generate, let's say, morphological variation in response to multiple design objectives, design problems, in order to solve complex, let's say, architectural issues and problems. And so I will first start with giving a bit of an overview of MTech, of the kind of tools and techniques that we use, and then how we elaborate on those tools and techniques, as I said earlier, for complex architectural problems. And our main kind of, let's say, interest is being able to use what we call, emergent technologies for emerging problems in the world, emerging problems in the real world. And those problems obviously, scale from, let's say, local material problems to architectural problems to urban problems to settlement, more kind of ecological problems in the world. And the last two thesis projects that I will show are trying to address a combination of these issues. And our kind of ethos is, this phrase that was said by the futurists around 100 years ago: every generation must build its own city. And the question that we always ask ourselves is, how are we going to build our cities of the future? And as I mentioned earlier, we try to aim for this kind of multi-scalar approach, where when we start with our students in the beginning of the year, we look at local material systems, we explore material systems, geometry, geometrical relationships, their analyses, details, tolerances, and so it's a very much iteratively generated experimental program. Sorry. And we really start with simple experiments, very much hands-on. We're a very much hands-on program. We start with paper, cardboard, so on and so forth, and really understanding the material properties, their curvatures, their limitations in terms of material properties, and exploring, so to speak, performative skins and various types of performance-based analyses. So they might be structural performance, obviously, environmental performance, and as I mentioned earlier, looking really into the tolerances, how components come together to generate 3D formations, so on and so forth. And of course, as our students advance in the program, I won't be talking too much today on this side, but robotic fabrication is one of our main interests. This is actually my personal kind of research agenda as well, robotic fabrication. So as we understand the behavior of materials, we then start to incorporate advanced fabrication tools. This is one of the examples that we have built in the past years. This was a combination of curved folding and robotic incremental sheet forming processes, and how the two processes can complement each other in order to increase the stiffness of sheet materials. And so in this case, where incremental sheet forming was employed was guided by the structural performance before it was employed, and of course a comparison of how the performance was enhanced after it was employed. And as I will show you later, we publish a lot of papers on these subjects, obviously our students as well. So definitely fabrication and materiality is something that we are really interested in, and how materiality becomes part of the larger kind of architectural and urban scale explorations. Again, as we advance in the program, we start to incorporate more advanced computational simulation techniques. We work with a lot with natural systems and biomimetics. That's one of the, again, ethos of MTech program. Genetic algorithms and evolutionary computation, as you will see later on. So there is a lot to learn from nature, obviously, and these kinds of advanced computational techniques, as you might know, are actually extracted from natural systems. They are based on natural systems, and how natural systems work and evolve. And so those are some of the techniques that we explore. In terms of biomimetics, for the past few years, we have been exploring social insects and their construction behavior and their life cycles, as well as their construction behavior. And we aim to extract and abstract some principles from these natural systems. And then we implement what we have learned, what we have abstracted from these systems for larger scale, let's say, architectural systems. And of course here, perhaps we can talk about this later in the Q&A session, but scalability is an important question that we always ask when it comes to working with natural systems. And it's a very iterative process, obviously. So it's a very iterative nature of experimentation and design, and it includes not only, let's say, working with these types of algorithms, but also analyzing the results and then feeding them back into the design loop. For us, we do not use analysis as a linear kind of evaluation tool, but we understand its implications and then try to implement those implications back onto the design workflow or algorithm. And of course, as I'm guessing you will all be familiar with, we work a lot with multi-objective optimization tools, both in the urban realm. We actually started working with them in the urban realm in the past. In this case, you are seeing the case of generating a tower design, but not only the tower design and also its neighborhood. But recently we have started to implement these techniques on smaller scales as well, such as architecture and local material systems. And those are the examples that I will be talking to you about soon. Some of these techniques are scalable, and that's what I will be talking about. And that kind of really brings me to our main interest in MTech. So studying real world problems such as the decrease in biodiversity, climate change, immigration patterns, sea level rise, so mainly ecological changes, so to speak, and then formulating solutions to these issues via local material science, architecture, engineering, and ecological settlement scale. And that really sets up the focus of our thesis dissertations. So our dissertations aim to constitute a novel architectural response to an existing design problem in the world that can encompass material, architectural, urban settlement, and ecological scale solutions. That's our main goal. And of course, the dissertation needs to contribute to existing knowledge, and that contribution can happen through novel material forms and processes, novel architectural and urban systems, or novel constructions, or a combination of all of them. what is the purpose of all of this? Obviously, to advance the existing understanding and quality of the built environment, and to publish what we have found out, and to be able to discuss the advantages and limitations of the research that we have generated. And, as I mentioned earlier, our thesis dissertations encompass several scales, including material processes, architecture, urbanism, and ecological engineering. Just a moment. Let me just, okay. So I have very kind of shortly talked about the technologies and the techniques that we employ in MTech. Technologies on, I mean, I didn't really talk about the AR, VR or XR part, but there is also something that we work with, our students work with, but advanced fabrication, AR, VR processes, advanced computation and simulation, and their analysis and evaluation. So before the dissertation starts, we have these kind of small modules where our students have the chance to explore these techniques and technologies. And then after the seminars conclude, then they start to explore which field they want to work on for their thesis dissertation. And so I'm going to be describing, I will be describing two theses from our recent MTechers that try to address ecological urbanism, architecture, and local material explorations on different climatic contexts, environmental contexts. And the first of those is reformation by Iso and Alina Koleva. Their main research question was, can a fabricated system of artificial reef structures support human settlement and provide adaptive ecological resilience? So their main, let's say, interest, their main problem area was, as you might be aware, as the sea level rises, a lot of homes are put at risk, and simultaneously vital coastal habitats are disappearing due to pollution and rising ocean temperatures. And so their main domain for their thesis focused on a coastal region in Indonesia. And their ambition, as I said, was to generate an ecologically resilient, multifunctional offshore structures for offshore living and urban living. Excuse me, not offshore living, but urban living. And so the first kind of field of exploration was to study these coastal areas, to study the nature of sea level rise in these areas, to study the wave implications in these areas, and to kind of understand the transition from land to intertidal zones to the reefs, and of course back to the ocean. So the thesis really worked on kind of multiple scales. First of all, it seeks to support an underwater ecosystem through a porous geometrical topology capable of occupation by marine life. So the thesis really aims to kind of integrate, excuse me, urban living and this marine ecological system through the reef structure and through the vertical urban living structures that they aim to enhance. Excuse me. So for that, towards that goal, first they started to work with these porous topological structures, exploring various geometrical forms, and of course their internal variation, and mapping how these structures could be distributed in the ocean bed according to the life forms that are living and their distribution and their density. So they analyzed the geometrical forms, as I said, according to how they can be distributed. And these structures were later on tested using CFD techniques to demonstrate their resilience to wave action. And basically, I mean, the objective of these experiments was to see how erosion of the existing structures could be prevented while maintaining a kind of dynamic and living coastline. Fabrication experiments were conducted, in this case using cast concrete, but actually their final proposal was not about using cast concrete, but this was just for fabrication purposes, for prototyping purposes, and they also explored how this fabrication technique could be, let's say, multiplied and could be automated. And as I said earlier, mapping the marine life forms according to the depth that they occupy in the sea and how their, let's say, sizes can affect the pore diameters and the concrete texture of the reef structures that they proposed. That was one of the main goals. And again, as I said earlier, mapping the density, the variation in the density of these structures horizontally and vertically on the site was one of the goals that they explored and analyzed. And of course, this also has some structural implications. This is one of the instances where they use multi-objective optimization because not only did they want to create these reef structures, but the other kind of main goal is to make them structural so that vertical living structures can be proposed. So their structural performance was quite important. While at the same time, they started to study on the site wave attenuation patterns, and the wind direction. Obviously, it's very important in this case. So understanding the wind direction, understanding the wave patterns and how those patterns can be attenuated. And so this formulated the second part of the, let's say, multi-objective optimization approach, where the design optimization in this case sought to look for candidates that could maximize the view field area from the housing units, the maximizing the annual sun exposure on the deck surface, minimizing the angle, the alignment to the predominant wind vector. So these are objectives that will, let's say, enhance the quality of human living in that area. And so that's how the distribution of the housing units was started to be generated. While at the same time, they studied the local human settlements in the area. And of course, these settlements have been built for centuries. And so, by nature, they work with the environmental conditions in the area. So the roof structure is very important. The local materials are very important. How the wind is captured and how sunlight is captured are very important. So those are some of the main parameters or goals that they worked with. And finally, using the data on the environmental conditions such as sunlight, wind, view field, like as I mentioned, and aspects relating to local architecture, guided the distribution of these settlements in the area. So this is a very kind of short summary of this thesis. And as I said, it was one of the first kind of attempts that we had on how to think about the material the architecture and, obviously exploring the local architecture, and also thinking about the ecological scale in this context of Indonesia, where sea level rise is a predominant feature affecting people's lives. Now, the second thesis that I want to talk about comes from a very different place. This is a recently completed thesis, Rural Waterscapes by Dev Ashok, Felipe Oyan, Jason Choi, and Yusra El-Shafei. Rural Waterscapes investigates the potential for the generation of a resilient rural community capable of harvesting and managing rain and atmospheric water in the context of an arid or semi-arid environment located in Ethiopia, Eastern Africa. Again, we start with the main research question: can a resilient design strategy be developed towards creating a self-sufficient rural settlement in Ethiopia's rural region, capable of harvesting fog and rainwater and managing its resources to respond to pastoral seasonal movement? In this region, as you might be aware, there's a lot of movement in terms of people, a lot of internally displaced people, a lot of refugees. So, the development of temporary structures for these refugees and internally displaced people, and its transformation from temporary to permanent settlements was the main objective of this thesis. So these are some of the main research themes. So water harvesting, obviously in this arid climate is very important. So how to capture water and fog, as I will show later on. In this region, access to clean water and food is very challenging, unfortunately, and the establishment of settlements, initially temporarily housing displaced people while managing the natural resources, and then, as I mentioned earlier, transforming these temporary housing settlements to more permanent settlements that are integrated with agricultural patterns was the objective. And while doing that, they also explored fabrication techniques through bioshotcreting, and how bioshotcreting could actually become the main actor of transforming temporary settlements to permanent settlements. So in terms of design strategy, there are multiple scales in this thesis and multiple areas of investigation. Agricultural patterns and livestock is very important, obviously housing, and the kind of interrelationship between the areas that are concerned with agriculture and livestock versus the areas that are for housing, the distributional patterns of the towers for capturing water and fog is very important. So there is this interrelationship between the towers, the architectural settlements, the agricultural lands, and the livestock lands. And as I said, there are multiple scales of investigation. So the whole investigation starts with a site analysis, understanding the environmental and climatic aspects of the site and gathering the data, which then informs the distribution of the settlement, which then informs the distribution of agricultural patterns. And from that point onwards, they start to explore the settlement distribution, and within the settlement distribution, the housing unit design and the tower design. And finally, exploring how the housing unit design can actually be fabricated by looking at local materials, and are there automated ways of fabricating these, as well as more kind of labor-based techniques, and what is the interrelationship between labor-based techniques versus advanced fabrication techniques. So as I mentioned, it starts with some fundamental analysis types such as water drainage, slope analysis, understanding the topography, obviously, and that starts to inform the first set of experiments on settlement planning. Now, this kind of line or polyline that you see in the middle is a highway. So they wanted, they thought it would be a good idea to place the public amenities as close to the highway as possible, while making sure that they respect the slope and the sunlight analysis, as I mentioned earlier. So the slope analysis informs, obviously, the water catchment areas, and they wanted to maximize the catchment areas in this case and maximize the search space as much as possible. So that defined the kind of larger scale settlement, let's say, location. And this is a selected site based on average fitness ranks. And then it starts to zoom in, really. So once the settlement area, once there's a successful candidate for the settlement area, then the next kind of task to do is to allocate the relationship between the housing area, the agricultural areas, and the catchment areas. So those are the three main, let's say, functional areas that they wanted to explore, using, again, multi-objective optimizational algorithms. And that led to, again, they used the average fitness ranks in this case. That led to a general distribution of housing and agricultural and catchment areas, as well as the foliar cultivation. And then again, we zoom in further into this functional distribution, where then they started to observe and study how the agricultural land distribution in this kind of more zoomed in, smaller scale area could be studied. And at this moment now, they started to explore, how the housing area is going to be allocated, how the towers are going to be allocated within the housing area, and its relation to the catchment ponds and the agricultural land. Now, I'm not getting too much into the detail of the agricultural aspects, but they studied various agricultural patterns and various types of land cultivation that are appropriate in this area. So I'm not getting into the details of that, but it's not all about these kind of pixels, so to speak, but they did do a very kind of thorough study of agriculture in the area. And further on, as I mentioned earlier, it starts to zoom in further, looking into the network generation between the various housing clusters and various public amenities such as warehouses, schools, so on and so forth. And these are all based on the data that they collected on how many people are expected to live in this region, how many people are temporary, how many people are expected to become permanently living in the area. So this is all based on this really quantitative data that they found. And as I said, I'm not going through that because that would take at least an hour to talk about. But in the end, they proposed, let's say, this initial planning where they distributed the water towers, lands, livestock lands, permanent housing, nomad housing, so on and so forth. And of course, the water tower is very important in their case. So they set up two experiments to study the tower. One is the more kind of functional experiment where they study, how to capture as much water and fog as possible. So it has a lot to do with maximizing the surface area that is exposed to the water. And of course, it is about exposure to wind, in order to be able to catch as much fog as possible. And the second experiment deals more with the structural aspects. And so they studied the integration of these two, let's say, functional and form-finding tools. So in this case, we're looking at the functional experiment where they're trying to maximize the catchment area, as I said, the surface area of the mesh, considering the predominant wind exposure and the surface area of the water collector. And in MTech, everything has to do with numbers. So, you know, these are the, this is the final analysis of the candidate that they selected. And then looking, and I'm proposing how this could be fabricated and assembled by people living in the area. So, I mean, of course, in MTech, we are very much interested in advanced and robotic fabrication techniques, but of course, it's very important to contextualize how these advanced tools and techniques can be actually used, or if they can be used in these kind of sensitive contexts. So in this case, they believe it makes more sense for people to put this together, that, you know, rather than a robot coming in and assembling things. We think that it's important to question the use and the contextualization of robotic fabrication. So in this scenario, people are coming together as a community and building their own water towers. And the same kind of approach applies also to the housing form exploration. There are some structural considerations that need to be explored, obviously, which will now take me to the fabrication approach. So first, it was a form finding experiment based on catenary forms. And first it was a single unit, then it was the combination of units. I mean, even though you do not see the site context here, they did pay a lot of attention to the site and the slopes that they could work with. And of course, in this climatic context, compactness is very important in terms of sun exposure. So that was that's why it was one of the main objectives they worked around with. And again, I am not going into too detail in this, but they studied the living patterns of the local people living in that area. What does temporary meaning? What does temporary living mean? What does permanent living mean? What is the kind of relation between temporary and urban living and the internal layouts and organizations of spaces that that variation implies? And studying the differences between the permanent and the temporary house. Now, the difference between the permanent and the temporary house relates to two main aspects. One is the internal organization, as I mentioned, and one is the structural implication. So before I get into that, they also studied how this land could be cultivated in time. Obviously, initially it's the arrangement of the temporary spaces, temporary housing units. And as time goes, obviously with the seasonal changes, the agricultural land distribution changes, and we start to see a change in the allocation of the housing units as well. And finally, that takes me to the kind of the fabrication logic behind it. So they initially studied deployable structures because, you know, obviously at first these are temporary structures. So in order to allocate for that temporary nature of the structures, they first studied deployable structures, but then of course the focus was on how to transform deployable structures through the layering of the initial framework, the thermal layers, the finishing, how to transform them into permanent structures. So the temporary structure really works with the initial deployable structure, and then the fabric formwork and the viscous layers. Of course, there needs to be a consideration for panelization in this case. which I will talk about in a bit, why they studied penalization. And then shotcreting is a process where these temporary structures can start to become more permanent. So that would be the final layers of application. And as you can see, they work with various material mixtures. They did 2 rounds of tests. One was manual shotcreting versus robotic shotcreting. And they kind of compare the 2 processes. So that's the tool that they developed for robotic shotcreting. And of course, you know, in this case, it was a case of, you know, studying the tool paths and the direction of the tool paths and the mixtures and the viscosity of the material and how it holds up once it's shotcreted. So this is showing some of those experiments with robotic shotcreting. But again, going back to my previous point, you know, these experiments are done indoors, as you can see, in a very controlled environment, right? Whereas in reality, they would have to be done in that arid context, right? So contextualizing the experiment, again, they decided that it could be more sensible for people to do the shotcreting, people in the community. So this shows the process diagram of how these structures are built, construction sequences, shotcrete by people living in the area. The deployable arches are removable once the shotcreting process is completed. So that kind of implies that they can be reused for other modules. And so, yeah, that really takes me to the kind of end of this part of the presentation. They had a kind of sensibility on the change of timescales and the change of agricultural patterns and the change in people's movements and how, you know, that can be reflected in the architecture. So that kind of takes us back to our initial research question. And yeah, as I said, exploring the change in population, the change in seasonality, and how all of those changes can be reflected in the architectures that we built. So yes, that takes me to the end of my presentation. Thank you for listening. And I just want to make a final note that all of this research work obviously makes sense if we publish it and if we share it with the community. So just kind of sharing a few screen captures of our research published in the past few years, both from us as a faculty and also our students as well. And yeah, thank you all. And if you have any questions, please, I'll be more than happy to answer.
Fantastic. Thank you very much, Elif. That was absolutely fascinating. Especially that last project. I can't believe how many, like the comprehensiveness of that project and the various scales, you know, going from urban to the very minutiae of fabrication. As you mentioned, takes a certain sensibility, but again, I think that really kind of brings home your original kind of premise of, look, you know, what is the scalability of what we're doing, and if you know, the fact that you can kind of demonstrate all of that, so many different skills in one project, is fascinating, absolutely fascinating.
Yes, and I mean, thank you, Mohammed, first of all. And I just want to add this. They did all of this experiments with shotcreting while we were in lockdown. So, you know, accessing the school, setting up the fab lab, and, you know, all of that, it was quite challenging. But I mean, they did it somehow. So, you know, that was quite fascinating for us to see, you know, the kind of enthusiasm for experimenting. And, you know, of course, we can discuss the kind of architectural outcome and the limitations and so on and so forth. But yeah, I mean, this is the kind of direction that we're trying to take in MTech. As you mentioned, applying these tools and techniques on multiple scales, but also questioning their scalability at the same time.
And so how do you see this progressing? I mean, I think, well, let me reframe that. First of all, a colleague from UTS might join us, landscape architect James Melson, and so also you might have a lot of questions to ask. But I guess one of the nicest things to ask about such initiatives is about the limitations.
Mm-hmm.
So what are your thoughts on kind of, where do you feel, look, sometimes there's a limit to this approach, something that has to change, perhaps a different alternative, and what could those limitations look like, perhaps?
In terms of the direction that we want to take, I mean, as I mentioned earlier, MTech is a very much kind of hands-on program, so it was very much about making and building. And then we started exploring, more kind of like urban explorations, urban problems in the environment. So I believe that we really want to explore this multi-scalar approach that I call, working with materials, but like really contextualizing everything and questioning, for example, the role of robotic fabrication or advanced fabrication in these very sensitive climatic areas. We have to be realistic about it. So I think that's the direction we want to take. In terms of the limitations, I would say that, when we look at the thesis, I guess the main limitation is time, because, there's, Master of Architecture lasts for 16 months, right? And so there's so much to explore, obviously, beyond that as well. I mean, this could turn into a PhD project. So I think the main limitation is time and how to synthesize what you can achieve in that period of time in a meaningful way. So,
yeah. Super. Yes, fantastic.
And I guess that applies to all programs of architecture, right? Because, you have to stop somewhere. So you need to know where to stop and how to stop, basically. So I think, that would be the main kind of.
I think where to stop is maybe easier than how to stop. How to stop is something that it took me 4 years of my PhD to finally figure out. Right.
Same with me,
do I know how to stop? Maybe not.
Yeah.
I'll kind of also open the floor for anyone who else wants to ask questions, or James or Dave, please feel free to jump in. So the next question that I kind of had lined up is kind of, do you find, so when kind of your students start to address a thesis question that tackles both urban and fabrication, two widely differing scales.
Yeah.
Are they able to apply that kind of complex thinking or the understanding of what they have learned throughout that process to both scales, or do they become experts at one over the other? So kind of what is the cross-disciplinarity here between these two, or between two scales that are widely different?
That's a really good question. There's no one answer to this. It really depends on the thesis and the area of investigation that they're researching on. Sometimes it's very much material exploration based, and also it depends on what they want to focus on and what they want to explore further. Sometimes, as you see in this final thesis I showed, it's a combination of the two. I mean, these guys really spare the time on exploring, the urban implications and architecture and fabrication. So it was really tightly kind of attached in their case, but it really depends on the system that they're exploring. So I wouldn't say there's one answer to it. It depends on, we don't force the students obviously to explore one realm over the other. We kind of guide them. But as I said, it really depends on the scale.
One question that I want to ask is everything has to do with numbers. I think that's my favorite quote. Sorry,
Yes.
Dave, I'm just gonna jump to you, but I have to raise this. Everything has to do with numbers. I would like to expand. This is for my students specifically. For those of you, and there's a lot of attendees for some reason in this lecture, which is a testament to you, Elif. But for my students and perhaps others, everything has to do that, because that's something that I also teach my students a lot, right?
Of course.
How do you, architecture is very or tremendously subjective. And
Yes.
I tell this my students a lot. In my studio, I might like your work. If you go to another studio, present the exact same work, they might not like it. Very subjective. And so what I tell them is actually when you start to transfer things to numbers and communicate through numbers, you've just found a medium to convey your ideas, to justify what you think is nice and what's not nice.
Yeah.
Can you kind of expand on that and what value you find there?
Well, I mean, that's also how we work, as you know, based on numbers.
That's where I learned it from, yes. So for those of you,
that's where I learned it as well. It's very much based on experiments, and this is what experiments are about. It's about, having input parameters, experiment, having output parameters, and what is the relationship between the inputs and outputs. And yes, of course, architecture is very subjective, and my view on this is, this is our approach. Our approach is based on experimentation and quantifying. And I think what's very important, as I mentioned at the very end, is publishing this, publishing the research and being able to share it with the community and, understanding their feedback on it. Dissemination of knowledge is very important. We base all of our research on experiments. I mean, that's how we have, how this program was founded, obviously by Mike Weinstock back in the day, and there are other pioneers in the field as well. Obviously, some people perhaps might not agree with quantifying things, but I mean, I respect that too. I think one interesting area that we could all explore is maybe looking at the unquantifiable or the more kind of experiential or the spatial experience related side of architecture and how that can be reflected in our experiments, so to speak. So perhaps the aesthetic qualities, the perception of space, and like I said, the experiential part of it, how that could be reflected through the experiment. That would be, I think that would be something we would explore further in the future.
Absolutely. Kind of the quality of space. Dave, over to you.
Thanks for a great lecture, Elif. Really nice to see the work. It's very jealousy-inducing to hear you learn.
Just also, Elif,
16 months with
sorry?
Just so that you know, Elif, also Dave works a lot with robotics as well.
Yes,
and kind of advanced fabrication.
Of course, I know.
And so
I've read a lot of your papers. Yeah.
Okay, great.
So you lament the 16 months. We of course lament much harder, 12 to 14 weeks we have with students. But it brings a question, which is, how do you, as a program, build knowledge beyond the lifespan of any individual student? And it's very interesting to hear you talk about, of course, the illustrious history of also the instructors to build knowledge beyond the lifespan of each instructor. I think that's something that's a really fundamental challenge for anyone like yourself running an informed program, to try to figure out how you pass knowledge from one to the next.
Knowledge. Yeah, well, that's a really interesting question. Thank you, Dave. My main response to that would be through the accumulation of publications in years, through the accumulation of books, articles. That's why, we as faculty have been publishing, throughout these years. Of course, in our case, there's, Mike and the other founders of MTech, they have published a lot in the past, but also in our case, you know, as Mohammed would remember from studio, we have a huge kind of library of thesis books. You know, the culture of the book is very important. And for students to be able to physically see those books and, you know, go through them, touch them, read them through, that's how knowledge is passed. So they see that culture when they enter the studio, or as in last year, because they couldn't enter the studio, we made them accessible to the students online, so they could go through all the work that has been generated through their peers, you know, in the past years. And so, for example, they take a look at one of the thesis dissertations, they are interested in the same research area, and then they advance on that research area, and they use that book as a precedent, or they use our publications as a precedent, and they build on it. So, I mean, sharing is really important, sharing the knowledge. I mean, that's why I keep saying it. You know, we do not, I mean, that's a very kind of cliche thing to say, but there's no need to reinvent the wheel every single time. Whatever knowledge we have to share it with the students. And I think that's how knowledge is passed through, you know.
Oh, it's a fantastic answer. Also because I love that it's not even within the thesis, of course, in this model of promoting that they reach each other's work is within the program, but I love that it's beyond that. It's that you're publishing genuinely to the entire community, not just to the program. That's really
and I mean, one more, maybe last thing to add, we encourage our students to publish because, you know, obviously they've come to study in this program, they are new to academia, right? So we encourage them to publish in conferences. We co-author papers with them so that we can guide them how to write an academic paper. And I mean, we love doing it, you know, we just, it's just what we love to do. So, and, you know, some of our students have then later on taken this route to do more kind of academic research. Some of them take PhD positions, so on and so forth. So, I mean, yeah, that's kind of.
Super. James, over to you.
Yes, thank you. Thank you so much for the lecture. Really incredible range of work, everything from construction, robotics, you know, wave dampening, foundations of buildings, and so on. So thank you very much for the work. So I'm coming more from the kind of landscape architecture spectrum of design, and I was quite curious how you see this, in some cases, very artificial divide, if you like, between these two disciplines, because in several of the projects, it was really clear that the area where architecture starts and landscape begins is more like a really complex Venn diagram or gradient rather than really distinct. So just how you, on one hand, perhaps as a two-parter, because I think that I'm sure there's plenty of students who have questions, and I'm really curious to hear what they ask. But also, as soon as you get into landscape ecologies, botany, soil science, erosion, especially just when you started talking about wave action, it's an area I've been quite familiar with. I mean, it's so complex. You know, where do you start? That's somehow maybe question 2. Thanks.
Thank you. So if I understood the question correctly, you're asking about how we start to explore these kind of complex areas and what is the distinction, right?
Well, the first, I would say the first question is, where do you see actually the role or even the usefulness of separating landscape and architecture as disciplines? Because it seems that you're actually often tackling both simultaneously. And then how do you actually deal with the complexity then that generates?
Right. I mean, we actually don't separate the two. We don't separate architecture from, let's say, landscape design, landscape urbanism, because, you know, our built environment is part of landscape, is part of nature. So this is, I mean, that's a really nice question you ask, because, you know, this is one of the main areas that, or the main themes that we want to inflict to our students, is that there's no distinction between what is called nature and artifact. right? So, and of course, it's a very complex area, you know, looking into larger complex patterns in landscape, in ecology, in ecological settlements. It's very complex. But what we work around with is that there is a notion of variation and complexity and gradients, as you mentioned, in the scale of ecology. So we do not distinct between architecture and ecology. And I think this is the direction that we will continue to work with, that there's no distinction between the two, that architecture is an important part of ecology and the main part of the, you know, why we are facing such climate crises and such, you know, disruptive changes to the environment is because, you know, for centuries, we thought that, you know, architecture is distinct from the rest of nature, whereas it's totally not. We are affecting nature, we're affecting environment, so we need to be very considerate towards how we build and where we build. And, you know, this is why, for example, maybe it might be a simple step, but okay, let's look at local materials. Let's reduce the impact of transportation of materials, you know. Let's really question robotic fabrication. So that's really how we approach it. And I don't know if it answers your question, but that's our main premise, that there's no distinction.
Absolutely, and I couldn't agree more. And I think it's self-evident in some of the outcomes of the project.
Yeah, I mean, just to add on that, I remember when I was in MTech, like that's spot on. We never really, like this idea of landscape and architecture was very new to me when I moved to Australia. I was like, okay, so they're separate here. Okay, that's cool. but when we used to apply them in MTech, they were, you know, what are you going to work on? Yeah, I'm going to work. And I don't even think the students really kind of distinguish between them. It's just one project, one umbrella that tackles all these different facets. And I think that's really kind of evident in the work. And also what's very evident is that they are reciprocal to one another. So the knowledge that they're gaining from the architecture is driving the ecological, and the ecological is driving the architecture. And so that really means that the students are not really finding a distinction between them. I'm very wary of time, so maybe I'll just end with this last question from Martin, and then Elif, your day doesn't start for another hour, so
No.
so I'm wary.
I can't keep going.
I'm wary of that as well. So the question comes from Martin. He's saying that, you know, the thesis projects and methods of approaching them with fabrication that you've showed were amazing, and we all agree. They also are very different and not a typical architecture project. Which is
what is a typical architecture?
That's my next question. So perhaps I'll maybe frame this. Let's say from here a 12-week architecture studio, right? So kind of you have a very clear brief, very distinct brief. So maybe also to contextualize that, maybe for the students that are here, you know, that a thesis project at MTech is a 6-month or sometimes more, right?
Yeah, at least, yes.
Self-driven, the students do whatever they want.
Yeah.
There are no elective or other things, right? Like they just focus all their time on the thesis project.
Yes.
So coming to the question, how does the program encourage research beyond architecture to multidisciplinary fields of interest, such as biology, psychology, and engineering, to begin framing these unique projects?
Yeah, okay, so before the thesis begins, so okay, let me give a very kind of brief summary. Students start in September. From September until the end of March, we have seminar courses and electives. Starting from April, thesis begins. If you're an MSc student, your thesis will conclude in the following September. So you have what, like a 4-month, 5-month period. And if you're an MArch, Master of Architecture student, it will be completed in January, following January. So you have 6-7 months. So the way that students are introduced to this kind of interdisciplinary domain is initially through the seminar courses. You know, our faculty includes engineers, for example. We work with biomimicry a lot, learning from nature, obviously multi-objective optimization techniques. I mean, all the kind of computational form finding and analysis techniques that we work with are taught to our students throughout these seminars. And, you know, it's also through the readings that we ask the students to go through. So that's also very much multidisciplinary, you know, computer science, engineering, biological sciences, so on and so forth. So I mean, as you also know, Mohammed, you know, the realm of biology is one of our main kind of exploration areas. And that also applies to engineering. And also there is a level of cross collaboration between various parts of the school. I mean, for example, you know, we held a workshop with landscape urbanism master's course. We are thinking of holding another workshop. So it's also about, you know, communicating with other programs that also kind of enhances the interdisciplinary nature. So yeah, I mean, that's.
Yeah, I think also, if I can add, if I'm not mistaken, MTech also accepts students from non-architecture backgrounds.
Yes, of course. Yeah, that's a very good point. Yeah, we've had engineering students, I mean, students with engineering backgrounds, various engineering, like even chemical engineering, for example.
Yeah, I remember that student. Yeah, like,
so,
yeah.
Or we had industrial designers, and, you know, that was a really nice experience because, of course, industrial designers have a very good understanding of making things, right? So when it comes to fabrication and prototyping, I mean, that was really fascinating to see, like another approach. Structural engineers we still have. So yeah, there is this kind of communication between various disciplines inside the program that, you know, when the students leave the program, when they, you know, go into practice, they can continue that kind of communication with other disciplines.
And so just because you said you have more time, Elif, I'm going to take you up on that and ask one more question. So Alexandra asked, and hi, Alexandra. And this actually, maybe James and Elif, both of you might want to answer this. So Alexandra comes from practice, and she's asking, you know, why does the integration between architecture and landscape work so well in research, which is, as James and everyone alluded to, seems to be a, you know, common sense kind of process to merge the two, but it's not really translating well in industry. And are there ways to remove this separation from industry and allow to, well, I guess the never-ending question is, how do you bridge the gap between academia and industry? Perhaps falls here.
Yeah, I mean, I think, of course, in the industry, I guess one of the main, let's say, challenges is time, right? You work with deadlines, and you also work with a certain budget, right? So, whereas in academia, you know, we can extend, we are more flexible, so to speak, in extending our deadlines, and we are more, in a way, more free to experiment with. And, you know, in practice, like you have multiple deadlines, and you have to just make it. So I guess that would be the main reason. Perhaps there's, you know, you cannot achieve everything that, you know, you can in academia in practice. But I think, I mean, I'm a bit more hopeful about the relationship between academia and practice. I think lately, at least, we start to see more collaborations between academia and practice. You know, again, there's a framework, obviously, for research, and there's a framework that is set up between academia and practice. Depends on, you know, what the research interests of both parties are. But I think we are starting to see more and more collaborations between industry and academia. So I see that as a hopeful sign. I mean, in the past, like, I don't know, maybe 5-10 years ago, we would always talk about, oh, there's this distinction between academia and practice, and, you know, why don't they recognize one another, so on and so forth. But I think we have started to see some collaboration emerging, and I think that's a good sign.
Yeah, I agree, but I think also it's quite regional. So Alexandra, I know, is based in Australia, so James works in Australia and he works in Europe as well. Australia is a little bit behind Europe, and I'm trying to be as politically correct here as I can by saying a little bit. Depending on who you're asking, they might disagree with the word little, but they are a little bit behind Europe in terms of perhaps bridging that gap. I don't know, James, do you have something to add there?
Yeah, I agree with the previous comments in that I think there's been a huge amount of ground made up just in the last 5-10 years. And I attribute that a lot also to the overlap of common language, metrics, in some cases even softwares becoming more and more common. So it was almost unheard of that engineers would be working on the same even softwares as the architects, you know, even 15 years ago. And now we are kind of in each other's kind of living rooms, kind of tweaking things and making mistakes, but at the same time having conversations which weren't actually possible because we just didn't speak the same language. And you can take that in many meanings. So I think it can and will come in Australia, and it can actually change quite fast.
Definitely.
And just, I mean, even just some of the work even of Supermaneuver, Dave here, other offices such as Maya Plemsas and Anna Abram. There's a lot of firms that very quickly are dealing directly with clients on large-scale projects in really interesting ways, I think.
I think what James mentioned is really important, that we have these common tools of communication, you know, between architects and other engineering practice. And if I may just add one more thing, you know, remember the InnoChain PhD framework, for example, where, you know, schools and offices collaborated to fund PhD research projects. I think that was a great initiative. And I wish that those kinds of initiatives proliferate in the future, that, you know, because that sets a driver for the industry and academia to come together. So, you know, I'm hoping that we will see more of that.
Super. I think we will end it here just because I promised everyone we will be done 12 minutes ago. And I need to be aware of everyone else here. There is perhaps just one very quick question. Does MTech offer a PhD option, Elif?
We have, as Mohammed knows very well, and also I, because we both did the same kind of PhD by design. So yes, I mean, it's called a PhD by design. So it's a little bit different from the PhD, like the more kind of, let's say, conventional PhD, so to speak. There's a design aspect to it, which is obviously generated through a lot of experimentation. So yes, I mean, we do offer that,
Super. And Felipe, if you do want to pursue a PhD, we would also be happy to discuss a joint PhD between UTS and MTech. Let us be the first ones to do it.
Definitely.
Super cool.
That would be great.
Well, again, Elif, this was absolutely fascinating. We really appreciate your time.
Thank you all so much for having me. I hope it was useful. Thank you.
Tremendous, absolutely tremendous. The attendee list is quite large, and so I think that's a testament to your work and to the work that you showed. I'd like to thank Dave, James, and Tim in absentia for also helping curate this and set this up and keeping the conversation going.
Really nice to see you all. Mohammed, thank you again. Dave, thank you. James, thank you. And also thank you to Tim. Thank you.
Super cool. Thanks very much. See you, everyone. And for those of you who are joining in the attendees list, be mindful that there are another 2 lectures in this lecture series. Keep an eye on the UTS Instagram page, LinkedIn, social media platforms, all that jazz for updates. Other than that, goodbye, everyone, and good morning.
Bye, everyone. Bye. Thank you. Bye, everyone.
See you later.
Bye. See you.